So it says evaluate the cosine of 30, the cosine of 90, and the cosine of 60. So what happens when you evaluate those? Cosine of 30, square root of 3 over 2. The cosine of 90, and then the cosine of 60, 1/2. And it says, does the cosine of 90 minus 60 equal the cosine of 90 minus the cosine of 60? So what you would say is, well, if I were to take this, the cosine of 90 minus 60 is actually the cosine of 30, right? Everybody see that? If you're doing parentheses first, that's how it works for all things. All right, so parentheses first. So the cosine of 90 minus 60 is really just the cosine of 30, right? And they're asking, does that equal this? All right, which I'm running out of room. So does the cosine of 30 equal that? Yes or no? It does not, right? If you were to take that, it does not equal, because cosine of 30 we said was square root of 3 over 2. Well, this is going to be, right, it's going to be not square root of 3. It's going to be, yeah, we're going to have something different there. So it's going to be 1 minus 1/2 or something like that. So the answer there is no. You have square root of 3 over 2, 0, and 1/2 are those three guys. And if I plug that in, I am not going to get square root of 3 over 2 equals negative 1/2. That's not true, all right? You'll notice that when you do all of these, the answer is no, all right? And so one of the things that we try to do with something like this is use almost a distributive property, right, with trig functions. We look at it and say, well, if I have the cosine of 90 minus the cosine of 60, distributive property, if this were multiplication, would say I can just distribute that cosine through. Distributive property does not work with trig functions, all right? Because the trig function is a function in and of itself, and order of operation says I have to actually do what's in the parentheses first, and then I have to do the trig function, all right? And so it's different than multiplication. That is not cosine multiplying by that. That is actually taking the cosine of it. And so I have to do what's in the parentheses first, all right? And that doesn't always work out the way that we want it to work out, because sometimes it's not going to be one that we naturally know. And so this lends us to the next identity that we're going to talk about, which is the sum and difference identities. They do a whole proof for you. It does stem from your distance formula on the unit circle. We're not going to do the proofs for it, but it does stem from that using the square root there. But what you'll find is there is a pattern that starts to come when you have the cosine of two angles added or subtracted, the sine of two angles added or subtracted, and the tangent of two angles added or subtracted. They're not hard to memorize, but you do need to memorize them. I want to point out a couple things here. For cosine, alpha and beta, those are just like x and y, all right? They're just variables, all right? So two angles. I have two angles added together. You'll notice it's cosine, cosine, sine, sine. Cosine of the first, cosine of the second, sine of the first, sine of the second. What I want to point out is the signs, and I don't mean sine as in cosine and sine. I mean positive and negative, all right? If it is plus here for cosine, it is minus inside the formula. If it is minus here, it is plus inside the formula. So this guy switches. Okay, does everybody see that? Alpha plus beta is cosine, cosine minus sine, sine. Alpha minus beta is cosine, cosine plus sine, sine. All right? That is how you break it up or put it together for cosine. So if I had 30 and 60, I would not just do the cosine of 30 plus the cosine of 60. We just saw that does not work, all right? I would say the cosine of 30, the cosine of 60, and if it were plus, I would say minus the sine of 30, sine of 60, all right? That's what I would do with that. For sine, the positive and negatives follow, but it's sine, cosine, cosine, sine, all right? So for sine of alpha plus beta, it is the sine of the first, cosine of the second, plus the cosine of the first, sine of the second. If it is minus, it's sine, cosine, minus cosine, sine. The positives and negatives follow each other for that one. All right, tangent's a little bit different. The top follows the plus and minus. The bottom does not. The bottom is switched. So for tangent, if I'm adding, I'm going to say the tangent of the first plus the tangent of the second over 1 minus tangent A, tangent B. All right. If I am subtracting, it's going to be the first one minus the second one over 1 plus the first times the second. All right. And so we're going to put these into practical use. We're going to actually do a couple of examples here. The first example we're going to do is actually proving the cofunction identities. Now you actually have these cofunction identities on your sheet. Cosine of pi over 2 minus theta equals the sine of theta. All right. So we're going to use our sum and difference to show these, and we're only going to do one of them for time's sake. All right. So for cosine, my rule says I can do the cosine of the first one times the cosine of the second one. And this is subtraction. So remember, it's flipped for cosine. I'm going to add the sine of the first one times the sine of the second one. All right. Now, what is the cosine of pi over 2? On your unit circle, the cosine, the x value of pi over 2 is 0. So this zeroes out. 0 times the cosine of theta. What is the sine at pi over 2? Y value is, for sine, 1. There we go. This guy zeroes out. 1 times anything is just itself. And there we go. The sum and difference identities work, all right, which we never doubted that they would. So this is just showing that these functions work with each other, right? So I have the cofunction identities that I am aware of, and you can see that using the sum and difference identities actually gets you the same answer, all right? So let's actually do it with some values, some trig values. Now I will say, they do this a little differently than I do this. And you're welcome to do it however you want. There are 2 ways to do it when it is in radian form. So I have 7 pi over 12. And they split it up into 3 pi over 12 plus 4 pi over 12. Well, why do we do this? Well, look on your unit circle and tell me if you see a 7 pi over 12. You do not, all right? And so this is going to be exact values, meaning we don't want you to plug it into a calculator and tell me what the trig value is for 7 pi over 12. I want an exact value, which means I'm going to have a radical in my answer, okay? My radical is my exact value. My decimal is rounded. So when I do this, I'm going to say, well, I need to break it up into 2 that are on the unit circle. 3 pi over 12 reduces to what? Pi over?
4.
Is that on the unit circle? Yes, it is. 4 pi over 12 reduces to pi over 3. Both on the unit circle. All right. And then I'm going to use my formula. All right. So if you go back to your sine addition, sum and difference identities, it's going to be the sine of the first, the sine of the pi over 4, cosine of the second. It's going to be plus because it's plus, the sign follows the positive and negative. So plus the cosine of the first, the sine of the second. And these are all on the unit circle. All right. So now we're just going to fill it in. What is the sine of pi over 4? Square root of 2 over 2. What is the cosine of pi over 3? We are really pulling our brains here, right?
1/2.
Yep, 1/2. Cosine of pi over 4. Yep, and sine of pi over 3. All right. And then I'm just going to simplify it. Square root of 2 times 1 is just square root of 2. 2 times 2 is 4. Square root of 2, square root of 3 is square root of 6. 4, because I have a common denominator, I can actually write it as 1. That's actually my answer. That is exact value. I can't reduce it anymore. If I could, I would, but I can't. There's no way to reduce that. That is my answer, square root of 2 plus square root of 6 over 4. But you'll see that repetitively with positives and negatives because of where you are on the unit circle. Now, if you're not great with radians, you could actually convert 7 pi over 12 to degrees if you wanted to and find 2 numbers on the unit circle that are in degrees that you're aware of. It just depends on how comfortable you are with degrees or radians, all right? Let's look at tangent of 15. First of all, is 15 on your unit circle? No, it is not. And so I want to use two angles that are on the unit circle that either add or subtract to give me 15. What are two angles on the unit circle that add or subtract to give me 15? 45 and 30. I'm going to subtract. Tangent of 45 degrees minus 30 degrees. Everybody see how that gives me the 15? And then I'm going to use my tangent rule. The tangent of the first one, remember the numerator follows it, minus the tangent of the second one, over 1, and this is opposite, plus the tangent of the first one times the tangent of the second one. All right, tangents are a little trickier, aren't they? So tangent of 45, that's actually an easy one. What is the tangent of 45? 45 is sine and cosine are the same, so the tangent is just 1. Tangent of 30, that's going to be 1/2 over the square root of 3 over 2, right? So we keep change flip, what happens? Square root of 3 over 3, yeah. All right. And then on the bottom, I have 1 plus tangent of 45 is 1, tangent of 30 is square root of 3 over 3. So you do have to do a little bit of manipulation here. I say a little. I use that term lightly. All right. So you do have to do common denominators here and then keep change flip, but it works out nicely, nicer than you would think. So my common denominator on the top is a 3. Right? So it's 3 over 3 minus square root of 3 over 3. So I have 3 minus the square root of 3 over 3. Everybody see that? And then on the bottom, same thing. It's just 3 plus the square root of 3 over 3. Anytime you keep change flip and the denominators are the same, it just ends up being numerator over numerator, right? Everybody agree? All right, so I end up with 3 minus the square root of 3 over 3 plus the square root of 3. The only thing is, I have a radical in my denominator. Pull back from your memory. How do I get rid of that? I multiply by what? That beautiful word that no one ever remembers what it is until I say it and explain it. It's actually the conjugate, but it's similar. It's just adding, right? It's just changing the sign. No one ever remembers that word. Conjugate, all right? Which means I've got to multiply the top and bottom by this conjugate of that denominator to get rid of it. Remember, when you multiply conjugates, it's the first one squared minus the second one squared. That's why it gets rid of your radicals, because a radical squared gets rid of the radical, okay? So you do need to multiply by your conjugate. That's why I said a little bit of manipulation. On the top, you're going to FOIL it. 3 times 3 gives me what? 9. 3 times negative square root of 3 is negative 3 square root of 3. 3 times negative square root of 3 is 3 square root of 3. And then negative square root of 3 times negative square root of 3 is just positive 3, right? On the bottom, I end up with the first one squared, 9, minus the second one squared, that's 3. All right? We're almost done with this little reduction here. All right, on the top, I have a 9 and a 3. That gives me a 12, right? And then I have a negative 3, that's a negative 6 square root of 3. On the bottom, I have just a 6. If it can come out of all of it, you can reduce it. What can come out of all of them? A 6. I'm emphasizing all of them because people reduce these incorrectly all the time, all right? But the 6 can come out of all of them. 6 can come out of 12. 6 can come out of 6. I end up with 2 minus the square root of 3. And that is my answer, simplified. All right, so it says find the exact value for each expression if alpha is in quadrant 3 with a cosine of alpha equaling negative 5/13, and beta is in quadrant 2 with the sine of beta equaling 3/5. They want the cosine of alpha plus beta and the sine of alpha minus beta. All right, so we do not know the angles. All we know is one trig function for each of these. And so the first thing you're going to have to do is you're going to have to know at least the sine and cosine of both angles, all right? Because the cosine of sum and addition and the sine of sum addition use cosine and sine of each angle. And we only know one of each. So I only know the cosine of the first angle. I only know the sine of the second angle. I need both to be able to do this, all right? And so I am going to go back to my Pythagorean identities to first figure out my sine and cosines that I'm missing. All right, and so if I look at the alpha angle, for the alpha angle, I have just the cosine. So I'm going to say sine squared of alpha plus the cosine squared of alpha equals 1, right? I'm going to use my Pythagorean identities here to first figure out what I am missing that I will need. And so we're just going to solve this guy. Sine squared plus 25 over what? 169 equals 1. All right, subtract 169 minus over 169 is what you're going to subtract it from. So the sine squared of alpha is going to equal 144 over 169. Sine. It can be positive or negative, but it told me some important information up here at the top. What quadrant is alpha in? So is my sine positive or negative? My sine is negative. So it's negative square root of that, which is negative 12 over 13. You could also use, by the way, if it's a Pythagorean triple, which is what this is, 5, 12, and 13, by the way, if you recognize those three, I don't know, maybe you do, then you would know that you could have opposite over adjacent, those as well work with Pythagorean. That's where the Pythagorean identity comes from. So you can also use the fact that you have 25 and 169, so obviously 144 is going to be your other side, which is going to be 12. So you can use your right angle trig here as well if you need to jump through that. So my sine of alpha is negative 12 over 13. All right, I need to do the same thing with beta, because beta I also only have 1. For beta, they've only given me the sine value, so I'm going to say sine squared plus cosine squared of beta, not alpha, equals 1. Again, I'm going to get the cosine squared of beta is going to equal 25 minus 25 over 25 minus 9 over 25, so 16 over 25. This guy's going to give me 4/5. I need to know if it's positive or negative. What quadrant is this guy in? This guy's actually in 2. What is my cosine value in 2? Positive or negative? Negative, so this is negative 4/5. All right, now I have everything I need to answer those two questions. All right. So the question is technically, I haven't even gotten to what they're asking me, cosine of alpha plus beta. So it's going to be the cosine of alpha, cosine of beta, minus the sine of alpha, sine of beta. That's how I would find that. If I know them, I just plug it in. Cosine of alpha, they gave me. Cosine of beta, I solved for. Sine of alpha, I solved for. Sine of beta, they gave me. Right? And then I'm just going to simplify those. This is going to be 20 over 65. Minus, and by the way, I'm not going to reduce this till I'm done because I'm going to automatically have a minus a negative, so it's going to be plus 36 over 65. I'll reduce at the end if possible. We're going to get 56 over 65, and I actually don't think that reduces. All right. So you'll notice I didn't reduce them individually because I automatically had a common denominator. So reduce at the end if possible. This one isn't. I would do the same thing here, just using my sign values, all right? So given one piece, you really have to solve for the other pieces before you can even move to your sum and addition, or addition and subtraction identities, your sum and difference identities. So when we're solving for this, first of all, pay attention to the fact that they said primary, which means I don't have to look at the loop. I'm just going to say with one unit circle, what are my possible answers here? Anytime you're doing this, you obviously want to get your trig functions by themselves if possible. And so what we're going to want to do here is we're going to want to split these up using our sum and difference identities first to see if we can get those out of the parentheses. And so I'm going to do the first one with the sign. This is going to be the sine of x times the cosine of pi over 4 plus the cosine of x sine of pi over 4. All right, that gives me that one. On the left-hand side, I have the cosine of x, cosine of 3 pi over 4, rather. Remember, it's opposite, plus there, sine of x, and then sine of 3 pi over 4, and then I have this random plus 1 there. All right, so we do want to plug in what we know and what we don't know. All right, if you have a trig function of pi over 4, you should know that. So this is going to be, and I'm going to put it in front like a coefficient. All right, cosine of pi over 4 is just square root of 2 over 2, sine of x. Sine of pi over 4, that is just square root of 2 over 2, cosine of x. I'm just putting it like a coefficient so it's easier to see. All right, 3 pi over 4, what quadrant am I in? Second, so what is my cosine value? Negative. Pi over 4s are all square root of 2 over 2, so that's nice and pretty. negative square root of 2 over 2, cosine of x. My sine value here is actually still positive in the second quadrant, so square root of 2 over 2, sine of x, and then plus 1. All right. When you're simplifying algebraic equations and you have the same thing on both sides, what happens to them? What's going to happen to that square root of 2 over 2 sine x? It's going to cancel because when I subtract it over, it cancels out. So these cancel each other out. And then I can move this guy over, right? So plus the square root of 2 over 2 cosine of x. Move him over. All right, I have square root of 2 over 2 plus the square root of 2 over 2. That is, and if I do it over here, I'll show you 2 square root of 2 over 2. That reduces to just what? Just the square root of 2. Square root of 2 cosine of x equals 1. Well, this is going to be a little simple. All right, what do? Get cosine by itself. Divide both sides by the square root of 2, right? Cosine of x equals 1 over the square root of 2. If I rationalize that, that is what? I'm going to find everywhere on the unit circle where my cosine is the square root of 2 over 2. It's positive. What quadrants will I be in? Cosine is positive in the first and fourth quadrant. So my x value is going to be the angle that gives that to me, which we already know is pi over 4. And then in the fourth quadrant, it is 7 pi over 4. Good? Questions on that? All right, let's try one.